For this video, we are going to go through a short little introduction to titrations, look at some of the lab materials involved and the vocabulary, and then we will do strong titration problems. So titrations are just taking place when you have a solution with a known concentration being added to a solution with an unknown concentration in order to determine the concentration of that solution here. And we can do titrations with acids and bases. So neutralization reactions are generally performed this way. So we did look at how to write neutralization reactions, and that was because we were getting ready here for titrations. So typically we have an acid being added to a base or a base being added to an acid here. What we use here to do this is we use a burette. All right, a burette is filled with a standardized solution. All right, standardized means you know the exact concentration of that solution. We'll talk more about standardization in lab, but you need to understand here that in order to do a titration, you need to be filling the burette with a standardized solution, and you've done lab procedures to determine the exact concentration of that solution. That's why it's been standardized. And you'll learn about this technique in lab. A burette is just a very large test tube, if you will, with all the graduated markings on it. You can kind of see one here. This is really short. Usually it's much taller. You can have an idea about what it looks like. But you can see all the graduated markings on it. There is a stopcock at the base that controls the flow of your solution out of the burette itself into the solution below. Typically, the solution below you're testing with the unknown concentration is going to be in a flask, and this allows for more vigorous swirling. So again, we'll talk about the basic setup here, and we'll definitely go through what you need to be doing with this in lab, but this is just giving you a basic overview here. But the key is the exact amount of solution you're adding from the burette into your flask is very important. And this is why you need to actually follow all the proper techniques for titrations, and you will learn these during lab. And these are AP testable. You need to understand the proper techniques and what could happen if you don't follow those techniques, how they could impact your lab data. So anytime we're talking about titrations here, we're just talking about taking our solution with a known concentration and adding it slowly here to a solution with an unknown concentration. And we can determine the concentration of that unknown using this process. This is just giving you a quick little preview here of the process and of the lab setup. But the basic gist is if you have your acid solution here that you don't know the concentration of, you pipette out a specific amount of it, right? And you would have to use one of these volumetric pipettes where we know the exact amount that we're adding. We put that in a flask, an Erlenmeyer flask here. Again, this is going to allow us to have more vigorous swirling without worrying about the solution kind of coming out of the flask. So we have our burette here, and we're going to need to clamp it to our ring stand. We will put our standardized solution into that. In this case, we're using NaOH in this picture. We have to record the initial volume reading of the NaOH in the burette. And then we have our acid solution in the flask below it. And then we'll open the stopcock and allow the solution to flow in. But there's even a procedure to this, how you do this, how quickly you let it in, and then when you slow it down. But this is all stuff you'll learn in lab. But you will need to swirl this as it's being added because this solution has an indicator in it, which will turn color when you reach a specific pH. All right. So your solution from your burette is being added into the flask. When you're done, you will record the final volume reading on the burette so you know exactly how much of the NaOH in this case that you added. And you can see here in your flask, it changed color to indicate that you were done. All right. Again, we will kind of look at all this in lab, but understanding here that we add an indicator to our flask so that we know when we're done and when the titration can stop. So this is just giving you a little bit of an overview here of the process and some of the materials involved. We definitely need to be familiar with the vocab here. The titrant is the substance with the known concentration that is added from the burette. All right, so your titrant is in the burette and you're adding it to the flask here. All right, this would be the solution that you have the known concentration for. It's been standardized and you know the exact concentration. The analyte is the substance you are analyzing. This would be the solution that's in the flask. All right, so you definitely need to be very familiar with these two terms. You could see them in problems. Titrant is what's being added from the burette, and analyte is what you are analyzing in the flask, trying to determine the concentration here. Some more important terms here to make sure you know. The equivalence point. This is a big one. The equivalence point in a titration is the point at which you have equal stoichiometric amounts here of acid and base. Essentially, at the equivalence point, the moles of acid equal moles of base. That's very important. Anytime you hear the equivalence point, you need to understand that the moles of acid equal the moles of base here. That's how you know you're at the equivalence point. You do need to watch for the ratio here. Sometimes these equations are not all 1-to-1, so you would need to watch for that in these equations. Just be aware, but most of these reactions we do involving titrations are 1-to-1. But the key here is if you are at the equivalence point, your moles of acid are equal to the moles of base. Okay, don't forget that. If you're at the half equivalence point, well, that's when you've added enough of the substance to convert exactly half of the acid or base into its conjugate. All right, so you've added enough here uh, of your substance in order to convert half of the substance. So basically, at the half equivalence point, something interesting happens. The pH at your half equivalence point will be equal to the pKa. All right, this is very important. If you can identify where your half equivalence point is, you know that the pH at that point will be equal to the pKa of your acid. So now you can get some information here about the acid, and you can get this right off of these titration curves, which we'll see. All right, so this is a big idea here that you need to understand. The half equivalence point is when you have added enough of the substance to convert half of your acid or base into the conjugate. And at that point, if you can determine the pH, you know that that's going to be equal to the pKa. And then you could use that pKa to even get the Ka of the acid here. And we already mentioned indicators. Just realize we add a few drops of indicators here to our analyte, and indicators will change color at a specific pH. And they're basically added to identify the equivalence point here. We try to use indicators that change color very close to where our equivalence point will be so that we know when our titration is done, essentially. So if you look here at this picture, this is just showing you how this particular solution, when you reach the equivalence point, it turns pink. We don't want to get a bright pink color or a deep, dark pink color because that means we went pretty far past the equivalence point. We want a light pink color. Even in this picture, it's probably a little bit too dark. A light pink color means you reach the equivalence point. If it's really dark, that means you've added a little bit more and you've probably gone past the equivalence point here. So your data is not going to be as accurate. All right, so we don't want dark colors when we're doing this. And it does take a little practice. Sometimes your first trial might be a little bit darker, but then you kind of know where you need to be, and then you can kind of get the next trials a little bit better. So we don't want to go too far past our equivalence point, but the indicator will tell us when we reach that point. And sometimes one little extra drop makes it go from light pink to dark pink. So you got to be really careful here. All right, definitely be aware of these big ideas here, especially understanding the equivalence point is the moles of acid equal moles of base, and that if you're at the half equivalence point, the pH is going to be equal to the pKa. I already mentioned this on the previous slide, but just be careful here. When we're adding the titrant to the end point, all right, we need to understand the definition of an endpoint here. The endpoint is the point in the titration when your indicator undergoes a color change. All right, we want that to be around the equivalence point. There's a difference here. The equivalence point is when the moles of acid equals the moles of base. But an endpoint is when your actual indicator undergoes a color change. So you definitely need to know what the endpoint is. All right. And it's very important, like we said, not to go too far past that endpoint. So if you're looking at your indicator, a lighter color here uh, is better. A darker color means you've added too much of your titrant and you kind of basically went a little bit too far past your endpoint, which probably means you're probably past that equivalence point where the moles of acid equal moles of base. So definitely understand that we would prefer a lighter color here for our indicator. Once it changes very faintly, that means we've reached that endpoint, and definitely know what an endpoint is. This is just giving you a picture form here showing you how this process would take place. But the basic gist, you would start adding your titrant from your burette into your Erlenmeyer flask. You'd be swirling this the entire time. Usually here, for the first trial you do this, you would add pretty fast initially. And then once you start seeing the color change here, you start seeing some of that pink staying around a little bit longer, you would slow it down. And then you'd kind of add it. And then once you reach your end point, right, you would stop. It would be a light color change. The first trial, you might go a little bit too far, but then you have an idea about how much of the titrant it's going to take to reach the color change. So then when you do your second and third trial, you can kind of go really fast until you get close to that amount being added from your burette. And then you can slow it down and go drop by drop because you kind of have an idea about how much it's going to take. And usually the second and the third trials, you get much closer to that light pink color. But that's what we prefer here. And again, you're swirling this flask the entire time so that the titrant as it's being added is being mixed here. All right, because usually where the titrant is it starts to turn color, but you need to mix it up. All right, in order for you to see that the entire solution has not turned pink. You haven't reached that endpoint yet. So we prefer that lighter color. Again, you'll be working on this in lab. You do need to understand the materials and the procedures involved here, though, with titrations. I want to talk a little bit more about these indicators here. We already said the indicator is added to the analyte in order for us to know when we reach that equivalence point because it will change color at a specific pH. These indicator color changes I already mentioned can be really fast, and sometimes one extra drop makes it go from no pink to light pink, and then one more drop goes all the way to dark pink. So you really have to be careful with this, and this is really in your technique to be careful and make sure you're reaching that light pink color uh, for your solution here when you're doing your titration. We want to choose indicators, though, that are based on the equivalence point of the reaction we're doing. Remember, we want to know when the moles of acid equal the moles of base. That's the equivalence point. Well, that's going to be at a specific pH. So we need to choose an indicator that is going to change color around the pH that we want. Okay, so that's very important here. If you look at this picture, you can see phenolphthalein in pink changes color here at a specific range, usually around 8.2 to 10. So obviously, if your equivalence point was much lower than that, you wouldn't want to use phenolphthalein. If you look at the picture here, methyl red, kind of this orangish color, changes pH or is effective essentially in this 4.95 to 6.0 region. So if your pH at your equivalence point was going to be much higher than that, then you wouldn't want to use methyl red because it would turn color much too soon. So the idea here, the big idea with this is that you want indicators that have a pKa equal to your pH at the equivalence point. All right. So if you know your pH at your equivalence point is, say, going to be 6.9, well, then you want an indicator that has a pKa of around 6.9. All right. Don't confuse this idea about the half equivalence point. If you go back a few slides, remember we talked about at the half equivalence point, the pH is equal to the pKa of your acid. That is not this. This is a totally different idea. They are two separate ideas, and you really need to be careful here. At your half equivalence point, if you can determine the pH at half equivalence point, that's going to give you your pKa of your acid, which you can then use to get your Ka of your acid. This is saying you identify your pH at your equivalence point, and then you want an indicator that has a pKa equal to that pH. Two different ideas here. This one is referring to picking an indicator that has a pKa equal to your pH at the equivalence point, and that's going to work best. So do not confuse these ideas and make sure you understand each of them. All right, so we need to choose suitable indicators here, and the indicator we're going to choose is the one that has a pKa closest to our pH at the equivalence point. So you might be given a list of indicators and their pKa's, and you would have to choose the one that's most appropriate based on the reaction or the titration that you're doing. So again, big idea here, make sure you understand this. We want the indicator with a pKa equal to our pH at the equivalence point. That's going to be the best indicator we want. When we are doing titrations, we can generate these titration curves. These are just graphs that have pH on the y-axis and the titrant added on the x-axis. All right, and these can be generated from your actual data using your burette, you recording, every so often, and then recording the pH itself, maybe using a pH meter or pH paper here, and you can generate these graphs based on the data. If you look at them, all right, let's just look at the one here on the left. The pH kind of increases slowly at first, if you notice, and then when you get closer to the equivalence point, it just jumps rapidly. That's why, like we said, one little drop can kind of make a big difference here, because around the equivalence point, the pH just drops rapidly, and then it kind of levels off here toward the end. So if you look at either of them, you can kind of see that. Initially, the pH kind of changes slightly, and then it kind of does a massive jump and then kind of levels off here. And you definitely need to be good with these titration curves, be able to read them, understand them, all right? You can look at this graph on the left, and you need to understand that this would be a titration of a base being added to an acid. So your base would be your titrant. That would be in the burette, and this is being added to your acid, which is in the flask. And the reason you know this is because if you look, your pH is very low initially. So if you're recording the pH in the flask, right, that's where you're recording the pH at, it's very low because in the flask is an acid. And then as you add your base and start to neutralize and destroy the acid, and then eventually reach your equivalence point, and you keep adding base, you go past the equivalence point, now it's more basic. All right, so you should be able to look at this and understand that the base would be in your burette and the acid is in the flask here. Notice you can identify the equivalence point in this picture. So when you see the big jump take place and then it goes and kind of levels off, in between, you try to find the area in the middle of that jump. That's your equivalence point. That's where the moles of acid equals the moles of base. And then you can cruise over and identify the pH at that equivalence point. But what's really interesting here, okay, if you go down to your x-axis, you can get the volume added here. This will tell you how much of your titrant you need to add to reach that equivalence point. So if you want to identify the half equivalence point, you take half of this volume, right? Let's just say it took, 20 milliliters here. You would know that when you added 10 milliliters or half of that amount, you'd be at your half equivalence point. So you could identify 10 milliliters here on your X, cruise up, you'd be at your half equivalence point, and then you can go over to the pH here, and then you would know that the pH at that point is equal to your pKa of your acid. So being able to understand these graphs and get information from them is very important. The one here on the right, this is an example of an acid being added to a base. All right, you're starting with a base in the flask because your pH is much higher, doesn't change much. All right, then it jumps, that's your equivalence point here in the middle, and then it levels off. Right, so you definitely need to be able to look at these curves, understand what you're looking at, have a general idea of what they look like, be able to identify equivalence point, half equivalence point, and so on. A little bit more here about these titration curves. Whenever you are doing a titration here and your acid and your base are both strong, your equivalence point is going to be at a pH of 7. All right, so when you're adding a strong acid to a strong base or strong base to strong acid, you automatically know the equivalence point is going to be at a pH of 7. So if you can look at one of these titration curves and see your equivalence point is at a pH of 7, you know that you were doing a strong titration. However, if you're using a strong acid and a weak base, your equivalence point here is going to be less than 7. Essentially, think about your strong one winning. The acid one is winning, so your equivalence point is going to be lower than 7 or more acidic. If you're using a weak acid and a strong base, think about the base winning. All right, your pH at your equivalence point is going to be greater than 7 or in the basic zone. You can also find pH here for these titrations at different points. We can do problems with this and actually find the pH at different points. And it's different. There's different, maybe set of steps here or procedures for doing this with a strong, and different kind of ideas for like when you're doing a strong weak. So today we're going to work on strong titrations, and then another video we'll look at weak strong titrations. Let's talk about the shape of this titration curve really quickly. So we already said that initially the pH is not going to change much. There's some changing, but notice there's no real jump. And basically, this is because of what we call a buffering action taking place. If you imagine this here, you have your analyte in your flask and you're adding some of the titrant. All right. Well, initially here, at least for a little bit, you have a large amount of that analyte in the flask, and you've only added a little bit of the titrant. All right. So the analyte is just annihilating and destroying any of the titrant that is added. Remember, this is going to be a neutralization reaction, acid reacting with a base. So as you're adding, say, the base from the burette, the analyte is just swarming it and destroying it, and it's not going to be able to change the pH much because you still have a lot of your analyte present. Okay, so that's why initially here we have this buffering, and you don't see much of a change in pH. There's just so much of that analyte. Any of the titrant that's added basically is getting destroyed, and it doesn't allow the pH to change much. At the equivalence point, we said the pH is going to dramatically change and increase quickly. So when you see this big jump, try to identify the middle area of the jump, and you'll be able to identify the pH here at the equivalence point. So you see a massive, very quickly rising up, and that's how you know you'd be at that equivalence point here. And then after you go past the equivalence point, you're continuing to add your titrant. So the pH will eventually just level off here. There's no more analyte present. It's basically now just the titrant. So you kind of end up at the pH of the titrant itself. So you can see here, looks like we were adding a base to the acid, because once we keep adding that base, we're kind of leveling off here in the basic region. Right, so this is the basic gist of what one of these curves looks like. You need to understand what's happening here kind of at all the points, and we can actually calculate pH here at different points on this curve. If we are looking at a strong titration here, all right, there's 4 regions of the curve that we need to kind of be concerned with here. And these are kind of the different areas where we could be focusing on the pH. So obviously, there's going to be this initial pH, all right? You're going to be able to determine the initial pH here of the analyte. All right. And then once you start adding titrant, so as soon as you add your first drop of titrant, up to until you get to the equivalence point, that's kind of the second zone. So you have the initial zone, and then you have kind of this second region between the equivalence point and when you added your first drop. Then there's, the equivalence point you could be worried about the pH for. And then anywhere after the equivalence point, we might have to look at the pH here. We know that the end point is the point at which the indicator changes color. Obviously, we want the endpoint to be very close to the equivalence point. The equivalence point is where the moles of acid equal moles of base. The endpoint is the place where the indicator undergoes the color change. So you definitely need to understand the difference between the two. We want them to be close, but technically they could be a little bit off here. But these are the four regions of the curve that we need to be concerned about and we need to look at here in order to be able to determine the pH. This slide, this picture is very important because it, shows whether or not you actually understand what's happening here kind of on a molecular or a particle level at each of the different stages here of the curve. So you need to kind of understand what's taking place. The first thing you need to realize is this is a titration curve for NaOH being added to HCl. Strong, strong. First thing I can look at here is I know this is a strong titration because if you see where the equivalence point is, it's at a pH of 7. We said when you have strong titrations, the pH is going to be at a pH of 7 at the equivalence point here. All right. And I know that we're starting with the HCl in the flask because I'm starting at a low pH and then it's increasing. So that means I'm adding the NaOH to it from the burette. All right. But look at what's happening here at each of the different parts. This picture here on the left is showing you the initial kind of what's taking place in the flask for the analyte. So if you notice here, all we see is that it's just HCl, right? Before we've added any of the NaOH, before we added any of the titrant, it's just HCl. And this is a strong acid, so it's 100% ionized. We don't see any HCl in there, we just see H plus and Cl minus ions. But then once we start adding the titrant, adding the NaOH, and this would be pretty much all the way up to the equivalence point, notice what we see now. Now we still have a large amount of that H plus and Cl minus because think about this. This requires thinking. You haven't reached the equivalence point yet. So that means you haven't essentially neutralized all of your acid. You still have a large amount of that acid remaining. So you still have H plus and Cl minus ions. But now you also have Na plus ions. All right. Think about the reaction that would be taking place here. That's important. You need to think about what's actually happening when the HCl and the NaOH are reacting. So if we take NaOH reacted with HCl here, we're going to get a salt and water. So you're going to get sodium chloride plus water here. Well, the water is just water. We're not showing those molecules here in the picture. Just assume that this is in water. But as soon as you add that first drop of NaOH, okay, you are now breaking down the HCl essentially and starting to form the salt, NaCl. So you still see the Cl minus there from the HCl, obviously, but now you're going to start to see Na plus ions in your picture. You might say, well, why am I not seeing NaCl together? Well, it's an ionic salt. It's going to dissociate, all right? So you need to understand here, from the minute you add one drop of your NaOH up to the equivalence point, you're going to have some H plus, some Cl minus ions present, right? Obviously, you would have more Cl minus ions present because of the NaCl and HCl both being there. They're both dissociating. That's kind of important. But you would also see Na plus ions from the salt that form. Notice then, this third picture now, you're at the equivalence point. Remember, at the equivalence point, moles of acid equal moles of base. Essentially, you've added enough of the NaOH to destroy all of the HCl. All right. So essentially, they both wiped each other out. At the equivalence point, the moles of acid equal moles of base, they wiped each other out. So you only have NaCl present at your equivalence point. All right. Understanding this idea that the equivalence point means moles of acid equal moles of base and they've completely annihilated each other is important. The only thing present here at the equivalence point is your NaCl. So you would only see Na plus ions and Cl minus ions. And you might say, well, why is the pH 7 at an equivalence point? Well, think about this. NaCl is a salt. It came from a strong base and a strong acid. Salts that came from a strong don't hydrolyze with water and they have a neutral pH. So this should make complete sense here why the pH at the equivalence point of a strong is 7. In a weak strong, it's not going to be 7 because you're going to get a salt that's going to hydrolyze with water and mess with the pH here. All right. But for a strong at the equivalence point, The only thing you have present is the salt that formed, the ions of the salt that formed because it dissociated. Once you add one drop past the equivalence point now, you need to realize that the NaCl is still there, but now you're basically all the acid is gone, all the acid is wiped out, so you're continuing to add NaOH here. So now you start to see OH minus ions being present along with the Na from the NaOH as well, but the salt is still there too. So you still have Na plus and Cl minus ions present. As you continue to add your NaOH, you would get more and more of these OH minus molecules accumulating here. And that's why then the pH, goes up to a basic pH, because now you have a large amount of OH minus present, and that would make sense that it's now going to be the base. So definitely, I would make sure you understand what's happening at all the points here. Initially, in between the first drop up to the equivalence point, at the equivalence point, and then after the equivalence point. You need to understand what you would see present here. You can easily be asked questions on this and need to understand this kind of on an ion level or particle level here, right? So this is definitely an important understanding here, part of your titration. If we were doing a titration here, and you can see from this problem, we're adding 0.10 molar NaOH solution from a burette into a flask containing 25 milliliters of 0.10 molar HCl. We're going to do this problem as an example here in a little bit here, but if you notice, basically we have NaOH in our burette and our flask has HCl. So again, knowing these strong acids and strong bases here are also important for titration, because now you know this is going to be a strong titration. Without even thinking about this, because it's a strong, you're going to have your pH for this titration being equal to 7 at the equivalence point. As soon as you know you have a strong titration, pH at the equivalence point is going to be 7. All right, so you could easily just look at a titration curve and know this would be a strong titration because your equivalence point is at that pH of 7. So as I said before, we're going to look at these 4 regions and see how to determine the pH here of a strong titration. We're only focusing on strong here at these different points. So the first place we're going to look at is how would you do the initial pH of the analyte for one of these strong titrations. Determining the initial pH here of a strong titration is very easy. So if here is our problem, okay, we are adding 0.10 molar NaOH solution from our burette. So our base here, our strong base is in the burette, and the flask has our 25 milliliters of the 0.10 molar HCl. Okay, if you want to find the pH initially of the flask, all right, we're not measuring the pH of the titrant, we're measuring the pH of the analyte. So we're trying to find the pH of the HCl. Well, if you want to find the pH initially here for any of these strong titrations, think about it. It's a strong problem, okay? If you're looking at even if it's a strong base or a strong acid here, you just need to take the negative log of the concentration of your H plus, and you can have the pH here, all right? HCl, all right, is a strong acid. You know the concentration of the HCl, therefore you know the concentration of the H plus, negative log of the concentration of H plus, boom, you have your pH initially. If this was a base instead of an acid, you'd have the concentration of OH minus, so you'd have to do the, pH plus POH equals 14 kind of conversion there, but it's basically the same idea. So when you're doing one of these strong problems, the pH initially of the analyte is quite easy. It's just a quick strong pH. If you know the concentration of the strong in the flask, as long as it's 1-to-1, you know the concentration of your H plus or OH minus. So you just do the negative log of that concentration. And in this case, if you were doing it for this problem, negative log of 0.10 molar would be 1. All right, so the pH initially here is 1. So this is how you would determine the pH initially of a strong titration. Now we're going to look at how you would determine the pH here of a strong titration from the point where you've added 1 drop of your titrant up to the equivalence point. So we're kind of looking at this area of the curve here. How would we determine the pH here? And obviously it's going to be a little bit more involved than our initial pH, right? Because now we've started adding our titrant here. So We still have our same kind of scenario here, but now I want you to find the pH after the addition of 10 milliliters of NaOH. All right, so I haven't reached my equivalence point yet. And sometimes in these problems, you don't know if you've reached your equivalence point. But in this problem, I know I haven't reached my equivalence point because, just an FYI, if I'm adding 0.1 molar NaOH to 0.1 molar HCl, both of those concentrations are the same. The reaction is 1-to-1. I know that until I get to 25 milliliters of NaOH, I'm not going to have the moles of acid equaling the moles of base here. So when I see I've only added 10 milliliters, I know that I haven't reached that equivalence point yet. All right, but you'll see that even if you don't know if you're at the equivalence point, you will know when you kind of start the problem here if you have reached it or not. So that's the good news. But I want to know the pH after the addition of 10 milliliters of NaOH. So I haven't reached the equivalence point, but I'm no longer at the initial pH. So I listed the steps here for you. If you need to reference back to these, definitely do it. But basically, you're going to get to a point here where you need to know how to do this. First thing you would do is you would find the moles of NaOH you added. Well, that's a pretty easy calculation. You added 10 milliliters, you know the concentration, you can determine the number of moles of NaOH you added. Basically, we're concerned here about that OH minus, essentially. Then you figure out the number of moles of HCl you started with. Well, again, that's a pretty easy calculation here. So you get the moles of NaOH you added, moles of HCl you started with. Because we're not at the equivalence point yet, I know that I'm going to have HCl left over. Essentially, you're going to take the one that's more minus the one that's less here to figure out how much of the one is left over. Basically, as you add the NaOH, think about this. This is a neutralization reaction. As you add the NaOH here, the acid is attacking it and destroying it all the way until you get to the equivalence point. So if you haven't reached the equivalence point, you still have enough acid left over that it is still destroying the NaOH you added here. So I need to figure out how much HCl is left. Then you use your total volume. That's key. You've added a certain amount of NaOH now, and you started with a certain amount of HCl. You use your total volume here to determine the concentration of H+. You have the moles of H+ from step 3, so you have your new total volume, get it to be moles over liters, determine your concentration of H+, then you can do the negative log of the concentration of H+ to find the pH. So let's actually walk through this math just to make sure you understand how to do this. The first thing I do here is find the number of moles of NaOH I added. And obviously you could switch the steps here. You could figure out the moles of HCl you started with first. That's fine. It doesn't need to be perfect with regards to that, but you need to figure out the moles of NaOH you added and the moles of HCl you started with. So again, pretty easy conversion here. Start with the milliliters for each. There's 1,000 milliliters for every liter. You know the concentration for each. Get your liters to cancel. So you know the number of moles here of NaOH that you added and the moles of HCl you started with. The good news is you might need the moles of HCl you started with maybe in another part of the problem, but you've already done that calculation here, so you would have it. If you look at this, I can immediately tell. Let's just say you didn't know if you were at the equivalence point yet. I can immediately tell here that I'm not at the equivalence point because if I started with this much acid, I would be at the equivalence point when the moles of acid equal moles of base. Well, I haven't added enough base yet to make that equal. Essentially, I haven't reached the equivalence point yet. So that tells me I have more acid left over here. That's why we need to figure out the remaining moles of acid that are still remaining here. Essentially, this HCl is going to attack and destroy, because this is a neutralization reaction, the NaOH that you added here. So the NaOH is going to be completely gone, and you're going to have HCl left over because we haven't reached that equivalence point yet. This is basically what I just said on the previous slide, but think about your reaction here. Sometimes it's actually helpful to write the reaction to make sure you understand what's taking place. I always recommend you write the reaction before you start any titration. But remember here, we had NaOH reacting with HCl, and we're going to form NaCl and water, salt plus water here. It's all 1-to-1, so that's good. But think about this. If you've added, okay, 0.0010 moles of NaOH, that's how much NaOH you added. That means it reacted with, because it's a 1-to-1 ratio, and destroyed the exact same amount of HCl. As you add that NaOH, the HCl and the NaOH are attacking each other. So if you added that much NaOH, that much HCl is now gone and destroyed because it's a 1-to-1 ratio. That's why we're subtracting the amounts here away. And that's what we're going to see here on the next slide. We're going to see how much HCl is remaining. Okay, since I know that this is the amount of NaOH I added, that's how much HCl is destroyed, but I still have HCl left over. So I take the one that's more here, the HCl, subtract away the NaOH that was added, and this is how many moles of HCl I have left over. I haven't reached the equivalence point yet, so the HCl is still there. All right. Remember, you formed some of your NaCl as well, but the HCl is the only one that's going to contribute to my pH here. So I now know the number of moles of HCl left. I'll take that and put it over the new number of milliliters. Remember here, you got to be careful. It's your total volume. I started with 25 milliliters. I added 10 milliliters of NaOH. So there's that many moles floating around in 35 milliliters. You got to convert the milliliters to liters so that you now are in moles per liter because that's your concentration. So essentially, this is your concentration, your 0.043 molar is the concentration of the HCl that's left. Well, remember here, this is a strong acid, so it's 1-to-1 here. If you know the concentration of the HCl, you know the concentration of the H plus to be the exact same amount. Now that you know the concentration of H plus, pH is negative log the concentration of H plus. When you do your calculation, the pH is now 1.37. So notice it hasn't changed much. We started at 1.00. We've gone up to 1.37. This makes sense. We have that kind of buffering action taking place initially. But this is how you would calculate the pH if you are at any point from adding the first drop up to the equivalence point. In this example, the acid is still there. You haven't reached the equivalence point yet. So notice you're still in the acidic region. All right, definitely make sure you can do this and understand the different steps in order to determine the pH at this point. Now we're at the equivalence point here. All right, so we've already looked at how to determine the pH of a strong initially. We looked at how to determine the pH when we have added one drop up to the equivalence point. And now we're going to look at the pH at the equivalence point here. We already know the pH of a strong titration at the equivalence point is going to be 7. All right. So they may not ask you the exact, they may not ask you to find the pH at the equivalence point. They might ask something like, how many milliliters of the titrant would you need to add to reach the equivalence point? And that's just using stoich here to figure that out. Here we can kind of use a little logic because they both have the same concentration. If I have 25 milliliters of acid, I will need 25 milliliters of base in order to reach the equivalence point. Because at that point, the concentration of H plus would be equal to the concentration of OH minus. Moles of acid equal moles of base. So it just depends here on the problem, but typically you're not going to be asked to find the pH at the equivalence point of a strong. You just know that it's 7. You might be asked something else like calculate the volume that you need to add. And we'll see problems like this, and you'll see that it's pretty much just doing stoich here. I just want to drive home that point that at the equivalence point, moles of acid equal moles of base. Essentially, you've added enough base here that the base and the acid have completely destroyed each other. Neither of them are present, and you only have your products at the equivalence point. Big idea of a titration that you need to understand. Moles of acid equal the moles of base at the equivalence point. Now we have one region left here that we need to look at for a strong titration, okay? What about finding the pH after the equivalence point? So after you get to your equivalence point, determining the pH after that point. Well, remember, once you reach the equivalence point, moles of acid equal moles of base here, right? So the only thing present after the equivalence point is going to be your titrant, essentially, all right? Obviously, the salt that forms is going to be there as well, but that's not going to contribute to the pH. So it's just the titrant that we added. Our original analyte has been destroyed because we're now after the equivalence point here. These are the steps you would follow in order to determine the pH after the equivalence point. So we want to find the pH after we added 35 milliliters of NaOH. Again, if you weren't sure, if you just got this problem, you're like, am I at the equivalence point yet or not? You would figure it out quickly when you started doing the problem. Once you determine the moles of NaOH you added and the moles of HCl you started with, you'd be able to see if you were at the equivalence point or not here. But we already know we're after the equivalence point. So these are the steps. It's very similar to what we did when we were in that region here from the first drop up to the equivalence point. It's just slightly different, but it's almost exactly the same. So you would need to figure out the moles of NaOH you added again, figure out the moles of HCl you started with. Again, you might have already figured that out in a previous part of the problem. And then because we're after the equivalence point, the analyte is gone. You'll see here that your moles of NaOH you added are greater than the moles of HCl you started with. So you're going to subtract to figure out how much moles of NaOH you have left over here. And again, you would see this in the problem. You just take the one that's more, subtract the one that's less. Let's just say you didn't know if you're at the equivalence point. You would quickly know it because you have more NaOH added than the HCl that was present. So you figure out how many moles of NaOH are left over, and then you put that over your total volume here again. Pay attention that you've added 35 milliliters. You started with 25 milliliters. That's a total volume here now. And you're going to need to figure out the concentration, moles per liter, of the OH minus that's still there. But then you'll need to figure out your pH from your POH. Because this is the concentration of OH minus, you will get a POH. So you got to get the pH from that. Very important to pay attention that now you're in the concentration of OH minus. So let's actually look at the math here and see what this would look like. The math here is pretty easy like we saw previously. You're just doing some conversions here essentially, but you figure out the moles of NaOH you added. All right, we added 35 milliliters, get to liters, and then you can use the concentration. So we added that many moles of NaOH, and then the moles of HCl we started with is the same as before. All right, so it's the same amount that we started with. And you notice here immediately, if you weren't sure if you were at the equivalence point, now you know. You added more NaOH than the HCl you started with. So I know by looking at this, I'm past the equivalence point. Essentially, all of this acid is going to be destroyed. Once you reach the equivalence point, your acid is gone, and now you've added extra of the NaOH here. Since we added 0.0035 moles of NaOH, that means all the HCl is gone. We've added enough to completely neutralize all of that starting value of HCl because of the 1-to-1 ratio in the reaction. So if we subtract, we'll be able to get the amount of moles of NaOH that are still remaining here. So when you do the math, all right, this is the amount of NaOH that we added. This is the amount of HCl that we started with. Essentially, just take the one that's more, subtract the one that's less, and then you know, okay, I have this many moles of NaOH left over. So there's that many moles of NaOH floating around now in 60 milliliters of solution. All right, we need to determine the concentration in order to do pH. So you know the number of moles, you need to get that over your total volume of your solution now. Be careful, make sure you get this to liters. Moles over liters gives us the concentration of our NaOH essentially. All right, this is the concentration of your NaOH, but because NaOH is strong and it's 100% dissociated and it's 1-to-1, if you know the concentration of the NaOH, you know the concentration of the OH minus. So now you can do your POH here. Be careful. Negative log of the concentration of OH minus. We get our POH 1.77. Again, if you stopped here, you would know this doesn't make sense because if you're after the equivalence point, you shouldn't be in an acidic pH here. It should be basic. So you know you have to keep going here to find the pH. Since the pH plus POH equals 14, if we take our 14 minus the 1.77, we get 12.23 for our final pH here. And notice this makes sense because it's in the basic region. We would expect at this point, after we added 35 milliliters of NaOH, we're past the equivalence point. We are going to be at a basic pH. All right, so that's how you would find the pH at any point from after the equivalence point here until the end of your titration. Just realize here, if you added a strong acid, all right, the strong acid here would be in your burette to the strong base that would be in your flask. It's just going to be opposite here. All right, it's going to be the same steps. It's just that you're going to be starting with a base, all right, in your flask, and you're slowly adding the acid. But basically, the steps are the same. Pay attention to which one you have more of still remaining. The curve will obviously look different. It'll start in the basic pH and then slowly go down to an acidic pH. But the pH at the equivalence point would still be 7 because it's a strong titration here. Just want to look at this summary slide. It can be very helpful here to make sure that you're kind of just processing all the big things that are happening at the different places. Remember here, the pH initially of one of these strong titrations is just the negative log of the concentration of your analyte. If your analyte is strong, it's going to be 100% dissociated. As long as the ratio is 1-to-1, just do the negative log of that concentration, and you can quickly determine the pH. Obviously, be careful here. If it's a base, you're going to get the pOH, but you got to find the pH from this. So that's what you would do initially. If you're at the equivalence point, because it's strong, the pH is going to be equal to 7. And then at any other point, find the moles of the acid, find the moles of the base, and subtract the two. You take the one that's greater minus the one that's less, and then determine the concentration of whichever one there's more of. Pay attention to your total volume, and then you use that to determine the pH. All right? This is a nice summary of basically what you do here for a strong titration. Make sure you can find the pH at any of these different points. So now I'm going to guide you through how to solve this particular problem. As you can see here, they're asking you to find the pH when the following quantities of 0.10 molar nitric acid has been added to 25 milliliters of 0.10 molar KOH solution. So for the first one, they want you to find after 24 milliliters of the acid has been added. Very important when you're doing a titration problem to actually write the equation first. So for this particular neutralization reaction, we have nitric acid reacting with potassium hydroxide. This is a neutralization reaction, so it's a forward arrow. And remember, you always end up getting a salt plus water for a neutralization reaction. So that's the particular reaction that we are actually doing here. Notice everything's in a 1-to-1 ratio, so that'll actually help us later on when we're solving this problem. So this particular problem is a strong base being titrated here with a strong acid. Okay, so the base itself would be in the flask and the acid would be in the burette, and you're adding it to the base. So the first thing we need to do here in order to figure this out, we have to figure out how many moles of base we actually started with here. So in this particular problem, there's 25 milliliters of the KOH, and we can convert that to liters here. All right, there's 1,000 mils for every liter. Our milliliters cancel, and then we know the concentration of the KOH. There's 0.10 moles of KOH for every liter. Liters cancel. Now I know how many moles of KOH I initially started with here. So it's 0.0025 moles of my base, my KOH, that I'm starting with. I like to label these things as I go through, just so that I, keeping myself organized, as some of these problems can be pretty long. So this would be the moles of base that I started with. So if I'm adding 24 milliliters of the acid, now I have to figure out here how many moles of acid I'm actually adding to this. Because remember, this is a neutralization reaction. I have a certain amount of base, I'm adding acid to it. As that acid is added, it's attacking the base and essentially neutralizing it. So I have 24 milliliters of acid. Convert that to liters here. And now that I'm in liters, I can use the concentration. I know that the acid is 0.10 molar, so there's 0.10 moles of the nitric acid for every liter.
And from that, I know that there's 0.0024 moles of my nitric acid that I added. Again, I like to label this so that I can keep my self going here and not messing up these problems. So I started with 0.0025 moles of KOH. I added 0.0024 moles of acid. So essentially here, think about what's actually taking place. Remember, from this particular reaction, this is a 1-to-1 ratio. Okay, so if I'm adding that many moles of acid, I am destroying the same amount of base. So as I keep going here, I know that I started with 0.0025 moles of the base. I added 0.0024 moles of the acid. Okay, so essentially what's happening is the base is destroying that acid. We haven't reached the equivalence point yet, so the base is essentially still winning out. So when this reaction is said and done, I have 0.0001 moles of the base, the KOH, still left over, okay, because I didn't add enough acid yet to neutralize all of the base that was present. So if I still have 0.0001 moles of the base left, it's now floating in, though, a total of 49.0 milliliters of solution. Remember, I started with 25 milliliters initially, and I added 24 milliliters of the acid. So my new volume at this point is 49 milliliters. So if I want to figure out the concentration of the base still remaining, I can convert this quickly. 1,000 milliliters for every liter. Now I'm in moles per liter. Okay, I know the concentration of the base left over here is 0.002 molar. And remember, this is KOH, which is a strong base, so it's going to dissociate 100%. Okay, so that means if I know the concentration of the KOH, I now know that this is the concentration of the OH minus because it's a 1-to-1 ratio. So now that I know the concentration of the OH minus, the POH is equal to the negative log of the concentration of OH minus. So the negative log of 0.002, which would be equal to 2.7. Remember, we only had one sig fig here, so we only want one decimal place in our pH. And this is POH, so pH plus POH we know is equal to 14. So 14 minus the 2.7 would give us the pH of 11.3. This should make sense. We haven't reached the equivalence point yet. Remember, at the equivalence point, it would be a pH of 7. We have added some acid here, but the base still remains, so we would expect a more basic pH for at least part A. So now to calculate part B here, after 27 milliliters of the acid was added, again, I need to figure out how many moles of acid I added here to the base. So I added 27 milliliters. I got to get that to liters so I can use my concentration. There's 1,000 mils for every liter. And I know that there's 0.10 moles of nitric acid for every liter according to the concentration. And from this, I know that there's 0.0027 moles of the nitric acid were added here. Okay, there is no need to calculate the amount of base that we started with. It's the same as we already calculated in part A, so there's no reason to do that again. Again, still a 1-to-1 ratio here. So because of that, we know that in this case, we now added more acid than there was base present. So we added 0.0027 moles of acid. There was only 0.0025 moles of base. This was the base we started with here that we calculated in part A. Okay, so essentially what happens is all that base reacts with the acid, but the base is essentially being used up. It's a 1-to-1 ratio. There's only 0.0025 moles of base available to react with the acid. So that allows us to subtract here and see that there's only going to be 0.0002 moles of acid left over here. So when this neutralization reaction takes place, all the base has been neutralized. We are past the equivalence point here, and we have actually added extra acid, 0.0002 moles extra. So when this reaction is done, there's 0.0002 moles of the HNO3 flowing around now in 52 milliliters of solution. Remember, we started with 25 milliliters. We added 27 milliliters. 25 plus 27 gives me 52. We can quickly convert this. There's 1,000 milliliters for every liter. This gives me the concentration. So my ending concentration here would be 0.004 molar. This would be for the nitric acid, but remember, this is a strong acid, so it's 100% dissociated. So if we know the concentration of the acid, it's a 1-to-1 ratio. So this is the concentration of the H plus. So if we want to find the pH of this, we know the pH is equal to the negative log of the concentration of H plus, which is equal to the negative log of the 0.004, which gives us a pH of 2.4, 1 decimal place because we only had 1 sig fig. So that's how you go about solving for this particular problem. Another problem is coming up. For this particular problem, it looks like we have a 0.10 molar solution of sodium hydroxide being put in a burette, and then using that to titrate 50 milliliters of a 0.20 molar nitric acid. So this particular problem is a strong acid being titrated with a strong base. So the acid is in the flask and the base is in the burette being added to the acid. Very important to write your reaction here. So we have sodium hydroxide, NaOH, reacting with nitric acid. This is a neutralization reaction, so we end up getting a salt plus water. And notice again, this is all 1-to-1, so this makes it very easy later on when we're doing our problem. The first part here wants us to find the initial pH of the acid solution. So remember, initially here in the flask, all you have is a strong acid. And because it's a strong acid, if you know the concentration of the acid itself, and it's a 1-to-1 ratio, you know the concentration of the H plus. So pH we know is equal to the negative log of the concentration of H plus. The concentration of the acid and the concentration of the H plus is 0.20. So negative log of 0.20 here gives us a pH of 0.70. So finding the initial pH of a strong titration is pretty easy. Just take the negative log of the concentration and you'll get your pH. Part B wants us to find the pH after 65 milliliters of the sodium hydroxide has been added. So remember here, this is a neutralization reaction. So when we're adding this NaOH, the acid that is there is going to react with it and neutralize it up until the point that the acid that is present is gone. So our goal here is to figure out, is there still acid left, or did we add enough base to essentially now destroy all that acid? So we're going to figure out how many moles of acid we actually started with. So we had 50 milliliters here of the acid in the beginning. So we can figure out the moles by getting to the concentration. So if we have 1,000 mils here for every liter, now that I'm in liter, I can use the concentration, which is going to allow me to get to moles. There's 0.20 moles of the nitric for every liter. Now I can see that I started with 0.010 moles of the HNO3, and this is the amount that I started with. I like to label these things. So if I added 65 milliliters of NaOH, let's see how many moles of base I actually added here. There's 1,000 mils for every liter. Now that I'm in liters, I can use my concentration to figure out the moles. In this case, though, there's 0.10 moles of the sodium hydroxide for every liter. So I actually added 0.0065 moles of the NaOH. So I can see here, okay, that I started with more acid than base that I added. So the acid is still going to win out here. I haven't been able to neutralize all of the acid. This is a 1-to-1 ratio again. Okay, so if I added that much base, I destroyed that much of the acid. So 0.010 moles of the acid I started with minus the amount of base that I added, and I actually end up having 0.0035 moles of the acid left over. Okay, I did not add enough base to neutralize all the acid. That's why I still have more acid remaining. And you can see there I messed with the sig figs a little bit. These numbers are pretty small, so I didn't want to round that up and change it. It changes the pH a little bit, but this is just a preference I had for this particular problem. Usually the numbers work out, but I decided to just go there to 4 decimal places and not cut off the number itself. So that's how many moles of acid I have left. So there's that many moles of acid now floating around in a new volume of solution. Remember, I started with 50 milliliters, I added 65 milliliters, so it's actually floating around now in 115 milliliters total. So I know there's 1,000 mils for every liter. This will allow me to calculate the concentration of the acid that I have left over here. I have 0.030 molar for the concentration of the acid. And remember, this is a strong acid, so if I know the concentration of the acid itself, this is the concentration of the H plus. So this is my concentration of the H plus that is still remaining. If I want to know the pH of that, I know pH is equal to negative log of the concentration of H plus. So the negative log of 0.030 is equal to 1.52. Okay, so I did not reach the equivalence point yet, so I haven't neutralized all of the acid that was there. I had some acid left over, and when I calculate the pH reflects that there's still some of that acid left over because it's a very low pH. Part C now wants me to calculate the pH after 150 milliliters of the base has been added to the acid. So I already know how many moles of acid I started with from part B. So now I want to figure out how many moles of base I added this time. So I have 150 milliliters of base that I added. I know there's 1,000 milliliters for every liter, and I know that there's 0.10 moles of the NaOH for every liter. So in this particular case, I added 0.015 moles of the NaOH, and this is how much I added. Again, this is a 1-to-1 ratio here. As you can see, we already calculated the amount of acid we started with. This is more than the amount of acid we started with, so there's going to be base left over. So 0.015 moles of base were added. I can subtract the amount of acid that would react with this. In this case, that's the amount of acid I started with. Essentially, all of the acid is going to be neutralized. Okay, it's a 1-to-1 ratio. So if all the acid reacts with the base, there would be 0.005 moles of the base left over. Okay, so we've reached and passed the equivalence point. All of the acid is neutralized, and there is just now base remaining. So we have 0.005 moles of the base, the NaOH, floating around in a new volume of solution. We added 150 milliliters to 50 milliliters, so that's a total of 200 milliliters. I know that there's 1,000 milliliters for every liter. This will give me a concentration here of 0.025 molar, and that is equal to the concentration of OH minus. Be careful here. The acid is all gone. The only part left over is the base. It's NaOH. So if you know the concentration of NaOH, you know the concentration of OH minus. So from the concentration of OH minus, we know that the POH is equal to the negative log of the concentration of OH minus. So the negative log of 0.025 is equal to 1.60. This is not the pH though, this is the POH. So pH plus POH is equal to 14. 14 minus 1.60 gives me a pH of 12.40, 2 decimal places, because we had 2 sig figs in our concentration. So that's how you go about solving the parts of this particular problem. Remember, this is specifically for a strong titration problem.